Hello, everyone. So I remember last time we were talking about a new topic, which is cardinality. Um, so probably today we'll go through some new topic regarding cardinality, which is the size of any set, and and we talk about some rules in it, like addition rule, and maybe we have talked a little bit about rule of the rule of product before, and today we'll continue about that. And so let's remember what we said, what we left last time. The product rule of two sets is like if the two sets are disjoint, then if we take their union, then their size union is still um the addition of the two sets cardinality altogether. So so that is usually the case. And now we extend this concept to some more general cases. So we will remember in previous lectures, probably we have talked about the pairwise disjoint set, which is like given some sets A1, A2, AN. And we say this set of sets, it is pairwise disjoint if for all I not equal to J for its index, then AI intersect with AJ is an empty set. So this is what we maybe we see before. So want to recover it today. And the extended version of the additional rule is that for a pairwise disjoint finite sets. So just mention here all of the AI, A1, A2, AN here, they are all finite sets. So we have not covered any information about infinite sets and no problem about them. So they are all finite sets, and then the union of them is finite. And we can just use the extended version of, I may forget about putting the cardinality denotion here, but it's fine. So it says like the union of any finite sets is if they're pairwise disjoint, then we can just sum uh each of its cardinality up and we get the same value. Okay. Uh, and some corollaries regarding that is if A and B finite, then A union B is finite, and A union B can be equal to A plus B minus A intersection with B, and A intersection B is also finite. So here, one difference between what we talked before and now is that we no longer have the uh we no longer have the condition that A and B they are destroyed or they're pairwise destroyed. So a very nice way to say about is we just minus it, but we still get same value. And this is only happening between two sets condition. We're still like trying to figure out what is going to happen for a general case of infinitely many sets. So how can we prove about it? The proving process, I would say, it uses some knowledge of what we covered in the set before about what's the property of disjoint sets and the property of the set difference and set union, something like that. So first we can write the union of two sets A and B in this form, x belong to A, x belong to B, in both, maybe it's or. So it's not and here, it's or. Yeah, and we can see that it is equal to A difference with B, union with A intersection with B, union with B difference with A. And this is, if we say a Venn diagram, we'll say that the first case A and this is B. The first case is here. The second case is here, and third case is here. They are all pairwise disjoint sets. And by the addition rule, if we want to calculate that, we calculate that cardinality and we get the addition of each of these sets because of their pairwise disjoint property. All right, once we found that, we can add something and minus the same set's cardinality in equation. So A difference with B. So let's see, these three terms are equal, and we plus A intersection B and minus A intersection B. And what happens is that this is the set of A, and this is set of B, and this is set of A intersection B. So why that's true is because A, for example, for the set A, is all of sets like X belong to A, and X belong to X belong to A by the destroying property. We can say X belongs to A and X not belong to B, union with X belong to A and X belong to B. And these two sets form a partition of the original sets A. So because they're pairwise disjoint, we just add them together. So we form A and plus B, and we get that result in N. So we proved it. So we prove this corollary result. All right, and we'll talk about, we brings about a new concept. So previously, all the cases like addition of two sets, addition of infinite many sets, cardinality, they are all addition rule. And this is the product rule, also called the rule of product. So if, for example, there are two sets, which is finite is very important because they're like, so why we can say it's finite? Because their cardinality we get a certain value. It's fixed, so it's finite. So if A cardinality is n, B's cardinality is n, then a Cartesian product with B is Mn. Or we can say like for A, because it's finite and cardinality is n, we can say it has n element inside, which is from A1, A2 to An. And then Bi is a set with each Bi equal to n. So Bi has, for each I, B has a certain cardinality as supposed to be here. And this is for all of the corresponding values here. And then the cardinality of the union of a single element times Bi is equal to n times n. And that's usually the case we found here. All right, so that's the case. And we'll give a brief proof about this case. So let's talk about the trivial case. So trivial case is not very general, but we can give us an intuition about it. So imagining A is an empty set, then the cardinality of A equals to M is 0. And A Cartesian product with B, because A is empty, and this set is also empty, because the first coordinate is empty, it cannot form any set with existed value. So A times B, the cardinality is also 0, which is satisfy the equality for all sets B. So in this case, it is true. But what about it is not trivial, like A is not empty. A has some element inside. And in this case, we can see that Si, we define a set Si equals to Ai times Bi. And Bi might just be set B. So you can just think about Bi is set B, but just have index to pair with Ai to form Si. In this case, because Ai is each element in A, and you only have maximum M. So this is the domain that I can be chosen from. So for all sets Si, they are pairwise destroying. They're pairwise destroying because all of the AI elements are different. So imagine like here, you have Bi n is equal to 2, then AI is for example, AI is 4, then 4, 1, 4, 2. This is the S Si, and Sj, A can be no longer 4, it can only be some other value, for example 5, 1, 5, 2. And these two sets is definitely destroying because they definitely have the different first coordinate, and that's why we can conclude something like that. So yeah, so in this case, we have found is pairwise destroying, and we can apply some rule we learned before. It's called the addition rule. So by addition rule, because Si is equal to the cardinality of Bi, because the single element adding into it doesn't change its cardinality, and still the Bi just increase its dimension from 1 dimension to 2 dimension, but the total length, the total size is the same. And then because all of the Si, they are pairwise destroyed, we can form this equation as our result, like A Cartesian product with B is equal to this one. And this one is equal to, because we can just like the union of it is just the sum of all of it, which is Si. And there's M sum, so which is M times Si, and each Si, the size is N, so it's Mn. So we have proved the result. And maybe some people will ask why this stage is true. And this stage is just like breaking A into this set and pair each element with B to calculate. So it's very reasonable. All right, so let's see some examples to make it vivid, not in the theoretical case. So the example in this, I think in this lecture is very, very basic. Maybe you already know from the elementary school, but you just use the rule of product and the rule of addition. So let's, for example, I want to estimate the typical goldfish laying in a pond. And for example, there's 100 goldfish in a pond. And our strategy is that we capture three goldfish, and calculate their average, which is like divided by the sum by 3. And how many different possibilities, different possible estimates are there? So by the rule of product, there's 100 times 99 times 98 different estimates, because the first fish we have 100 choice, the second one we have 99, because we capture them simultaneously. We don't replace each fish back to the pound. So there's 99 for the second choice because one is already chosen, and there's 98 choices for the third one because the first two are already picked. So that's this is also called a sampling without replacement. And what's about sampling with replacement is that we still capture fish, and it's the same pound, the same number of fish, 100, and we use the same method of estimate to capture 3 fish and calculate their average length. But in this case, we are not capture them simultaneously. We capture them one by one. We capture the first fish, put it back, capture the second one, put it back, and then capture first and then put it back. So in this case, the second choice have 100 values because the first fish is put it back. And this is called sampling with replacement, and this will lead us to the 10 to the power of 6 different estimate totally result. Cool. And we have talked about ordered pair, right? The ordered pair is an ordered set. It's a set with the property order and repetition, because it can replicate the two different coordinates. So that's called an ordered pair. But what about we have more than two ordered pair? We cannot call it pair, and we call it n-tuple. So for each element AI, if I is belong to 1, 2, 3 to n, the order sequence A1, A2, A3 to AN is called n-tuple, which is a set of n elements, and its repetition and order matters. So we said the basic set only storages the the elements inside the set. So set doesn't have order, sign doesn't matters about repetition, but n-tuples matters. For example, we can say 1, 3, 9, 5. If we order them by 1, 3, 5, 9, then it's a two different tuple, right? And why repetition matters? Because 1, 3, 3, 3. This one is not equal to 1, 3. Well, but for sets, they're equal, because sets, the three together, they're just equal to one single value. But in the n-tuple, it's different. This means it has four coordinates with a 4-dimensional one, and this is 2-dimensional one, which is absolutely different. And this is our definition for n-tuple. And for the sets using n-tuple, there's one very good example, which can extend our result of like multiple rule of product into more general cases. So in this case, we say, well, for each element AI, for all the sets A1, A2, A3 to AN, their Cartesian product A1 times A2 times A3 times to AN is a set of all n-tuples, A1, A2. Okay, so remember, previously we say if there are two sets A and B and their Cartesian product A times B is the set of all order pairs, and now becomes untouchables because it has absolutely more than two coordinate here. And we'll give a corollary of the product rule of two sets is there's n sets and all they are finite, and finite is very important here, and they're all finite, and we can calculate their cardinality by a1 times a2 times a3 times 2an, and this is and it's just like the multiplication of each cardinality of each set in it. Let's see another example. So it's very similar to the telephone number. The automobile license number is made of 7 characters, exactly 7 characters, or to make it more clear, it's chosen from English alphabet A, B, C, D to Z, or numbers from 0 to 9. So there's 26 English alphabet and only 10 number digits. So if 3 consecutive characters are letters and others are numerals, then how many possible positions for the automobile license number? So let's consider this one. There's, because it's exactly 7 numbers, so it's 1, 2, 3, 4, 5, 6, 7, right? And we know in between 3 of them are letters and remaining are all numbers. Because they're consecutive, so there's only this place can be a star, this place can be a star, can be a star, can be a star, can be a star, but this place cannot be a star, and this place cannot be a star because we start here. It cannot have 3 consecutive letters. So there's 5 choices of how the consecutive letters are started at. Then we are consider about so that gives us 5. Yeah, so that's like 7 minus 3 minus 1, which is 5. Okay, and how many possible cases for each of these conditions? Because there are 3 letters, the first is 26. It can repeat because like the number 911 has 2 1s, so it doesn't matter if it's replica or not. So the second is 2 half 26, the third half 26, and for the numbers, it's just 10 plus 10, 10, 10. There are 4 positions for the number, 3 letters, 4 numbers, and we times 5 of them together to get totally such number of possibilities. And this is our result. And the second case is like if we consider the lesson number still had rule, they are still chosen from the English alphabet and the number digit from 0 to 9, but they are not exactly 7 digit. They're not exactly 7 characters. They can be any they can be at most 7 characters. So in this case, it can have 1 character, it can have 2, can have 3, can have 4, can have 7 too. So it has 7 cases. We will treat them separately, and how can we use the product rule to solve it? Because each position we have how many? We have 36. We have 36 choices, and the second place 36, third place 36, fourth place 36. So it's just like 36 to the number of n for the n characters. And then we'll use the addition rule to add them all together because they are destroying numbers because their total length is different. So this will give us this many possibilities for this rule of forming the automobile license number. Okay, and we'll see something different here, I think. Okay, so let's move to compare sets cardinality. So previously we have talked about how to compare finite size, finite sets. It's just like if one set have more elements inside, then it's have larger cardinality. But for infinite sets, we may not we may not easily claim which set is larger because we don't know its total size. So how to compare it? There's one very common strategy, and it's a very common definition lead by ancient mathematicians. So if we can find an injection from A to A, from A to B, then we said A is usually smaller or equal to B's cardinality. And if we can, and they're equal if A is equal to B's cardinality. So I would say this property is not very useful, and we'll see later. And we say A is smaller than B if we can find injection from A to B, but we cannot find a bijection from A to B. So in the second statement, maybe we'll say we can find a bijection from A to B. Okay, so this is, if we can find a bijection from A to B, we say they are equal. And only injection is smaller or equal. And only injection, but we cannot find bijection. We prove these two at the same time. Look at the end here. Then it's small. All right, so maybe we'll see one proof here. So prove the first one. Suppose A is equal to N and B's size is M. Then there exists two bijections. This is by definition. If A's cardinality is N, then N, yeah. Let's see, maybe yeah, maybe A we change A into N, B into N. And in this case, like this must be a bijection, this must be a bijection. And because M smaller or equal to A, then like we'll see smaller equal. Okay. Because first we can suppose it's smaller or equal to, right? And if it's smaller or equal to, then all of the element inside set A, we can have another element B. We can just match it because and B is unique because M is smaller than. So this is an injection because like for all of the B, like A1 equal to A2, but B1 is not, but B1 must also equal to B2. So that means it's an injection. And in this case, we say the mapping, we can map, this is a mapping of injection from A to B, which is see how it goes. So inverse F maps A to NM. And this case is a bijection. And NM to NN. And this we say here, H, this is convertible F1 inverse, and this is H, and H is an injection. And from NN to B, which is here, which is conducted by G, and G is bijection. So overall, it's an injection, right? So injection. So we have proved the okay. In this case, we have proved this direction. If it's smaller or equal to, then there's exists an injection. So what's about conversely? Conversely is very similar. So suppose this is an injection, then there exists an injection in this form because F and G is still defined here, and this defined as from A to an M. This is from an M to A, and this is from A to B, and then from B to NN. So if this is an injection, then this is also injection because it's bijection, injection, bijection, which is also injection. So which is implied like N is smaller or equal to N. And this is from the last lectures. theorem when we talk about if there's an injection between two sets, then the domain set is usually small or equal to the range set. So we have proved this direction, and we are done here. Okay, and the proof of the second, if you hear like the second is equal and bijection, it's very similar. Just change small equal to by equal to and injection by to bijection, and you can prove it by yourself and look at Google to search if you are not certain about it. Okay, so the consequence of previous theorem is very important because it provides us a way to calculate cardinalities and compare cardinalities between infinite sets. So from now on, if we talk about let's compare to infinite sets cardinality, we just like to find if there's bijection or not, if there's injection or not, or if there's only injection and not bijection, and we can say something about two infinite sets, which one is larger and which one is smaller. And there's a theorem called Schroeder-Bernstein theorem, which is also called the SB theorem, and it's very close. It's very close to what we have talked about before. So this theorem says for any set AB, not only finite, but it can also be infinite. And in this case, if the cardinality of A is smaller or equal to B, and B is also smaller or equal to A, then it has to be A is equal to B, or their cardinality is the same. And yeah, so this one is very similar to the set comparison, like say A is a subset of B, B is a subset of A, and then must be A, B are equal. The sets are equal. So this is the SB theorem. And the next one is the properties of some cardinality comparison. If A is smaller than B, B's cardinality is smaller than C's cardinality, or there's one smaller, another is smaller equal to, or smaller equal to, another is smaller, and then we're gonna say the smallest one in this one, A is strictly smaller than C, and this is the property which is very easy to understand. And yeah, so today we will bring about a theorem which is called Cantor's theorem, because it's all bring about by Cantor, but the two are not linked at all. So Cantor's theorem 1 and Cantor's theorem 2, they do not have relationship regarding each other. And the first theorem is stated here. So if S is a set and its power set is PS, this one, this is its power set, then the cardinality of the set S is smaller than its power set's cardinality. Well, so to prove this, we just need to find by the previous theorem we learned, we just need to find there's an injection from S to P, but not a bijection from S to PS. So this is our goal. Okay, so how can we do it? So first, let's do a empty set case to see what we can gather some information from it. So usually when we have no idea about how to do a proof, we just see the very, very basic one. So in the set problem, usually the empty set. So if S is a empty set, then PS is what's PS? PS is a set of empty set which have one element. So it's 0 and 1. And because they're finite set, then S is smaller than PS. But we can also say, because this set is empty, this is not an empty set, we cannot find a bijection from 0 to 1, right? Because their number is different. However, we can find a injection from this one to this one. Why? Because there's no element. So the function can be any function. And some of it, there must exist one injection function. It's just that we cannot take any element from empty set to this set. So we can prove there's injection but not bijection. So for more general cases, we define a function from S to power set of S. And function is like fx goes to a set of x. Then this is an injection, right? This is absolutely an injection because because if X is equal to X2, the set version, and this leads to the inner element, the two must be equal. So this is true. And we find, because we can always find injection, then we say S is smaller or equal to power set of S cardinality. All right, so we have proved half of it. We just need to prove like we cannot find a bijection of it. So how can we do about that? If we want to find there's no bijection, we might first assume there's a bijection, right? We can assume there's a bijection goes from S to PS, and we just need to find a contradiction if reach to a situation that's impossible or is like contradicted to some axiom, then it's over. So if there's a bijection from S to PS, then for all x in X, fx belongs to PS. So fx is a subset of X. That's the definition of the power set. And in this case, for all of the X in S, X might belong to fx or X not belong to fx. So let's define new sets, E. Define sets new set E here. So E is that all the X belong to S, and X is not belongs to fx. So this leads us to think about something we call Russell's paradox. But this might not be a Russell paradox because we already find X as here. So X can only be chosen from S. And because X is picked from S and it's a bijection, so E must be in the S subset, right? Because it's a subset of S, so it's in the set of power set of S. And because F is a bijection, so for all element Z in S, then FZ is in E, and this is from the definition of bijection. So now we reach a contradiction here. So the statement of Z belongs to E leads to a contradiction. So why is that? Because now if we consider what Z belongs to E mean, Z belongs to E means Z is not belong to FZ. Yeah, there's a writing error here. It's not belong to FZ, which means like if not in the FZ, then FZ is equal to E. So it's also said Z is not belongs to E, but here Z is belong to E, and is if and only if. So this is a fact which belongs to which leads to a contradiction. All right. And finally, so such bijection from S to PS doesn't exist. So we failed it. All right. So no bijection, but only one injection. We can find at least one injection, which means S is not equal to PS, the cardinality level. So which means like the S cardinality is smaller, strictly smaller than the power sets of S cardinality. And we are done here. And we're moving to the central topic of today. We have talked about finite set, we have talked about infinite set, and now we need to classify the set of infinite set again. So yeah, there's one corollary before, which means like n is smaller than Pn, smaller than P, power set of n, smaller than power set of n. So the previous theorems, the Cantor's first theorems corollary is this one. So let's talk about countably infinite. So if S is any set, and there's one bijection, F goes from S to N, which means it has the same cardinality as the natural number. Then we say S is countably infinite. And the countable sets, and what's countable sets? Countable sets include the finite set and the countably infinite set. So it's countably, it is countable. And any set that is not countable is called uncountable. So we can give a graph like that. So this rectangular larger one is called sets, and sets can be cut into uncountable and countable. And countable set we can also divide into countably infinite and finite. And countably infinite must satisfy this condition. And this is bijection. So this is the classification of sets in the aspect of cardinality. Okay. So we'll give one example here to mean what does like countably infinite mean. So because by definition, if a set is countably infinite, there exists a bijection goes from S to N. But what about a set S is N itself? Then it must have a bijection from N to N. So all of the natural number is countably infinite by its definition itself. And now we want to show in the example the set of integers, the Z, is also countable, which means and we definitely know the set of integers is not finite, so it must be countably infinite. So we'll first prove it by constructing one function that is a bijection from let's say from N to Z. So we can construct a function f goes from N to Z, where N is a set of natural numbers and Z is a set of integers. Okay, and now we define something here. We define for all of the elements in N, Fn is, if N is even, it's equal to N divided by 2, and if N is odd, is equal to the minus N minus 1 divided by 2. And this is actually a bijection because we can show a very interesting story. So it goes from the smallest N, because by the well-ordering principle, it must have a smallest element in it. So it goes from the smallest to largest to see what this definition is. So f1 is equal to 0 because 1 is odd, and odd 1 minus 1 is 0, so it's 0. 2 even, so 2 divided 2 is 1. 3 odd, so it's 1. It's 3 minus 1, which is 2. Negative 2 divided by 2 is 1. And we continue this trend whatsoever. It's like 1 maps to 0, 2 maps to 1, 3 maps to minus 1, 4 maps to 2, 5 maps to negative 2, 6 map to 3, and it goes on. So the mapping of the mapping of the natural number is going to 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, and this trend is going to the infinite, which means like all of the integer is covered by all of the natural numbers. So so this is a bijective function. And by definition, this is countably infinite, which is also countable. And there are some interesting ideas regarding the countability of sets, cardinality. So a theorem says like if A and B, there are two countable sets, then A union with B and A times B are also countable. And I do not provide proof for this too, but it does have proof. But some like easy idea to think about is like if A and B are countable, then the union, if they're pairwise, is adding them together. And adding them together is just like adding the negative and positive side of the natural number, which is integer, right? And times, which means like if one dimensional x is countable, then the second integer dimension y is just like there's many countable, and this is also many countable, and we just time together, which is at the same cardinality, which is also like countable many points there. All right, and some corollaries are following before in the lower part. So the first corollary is if there's n set of A, which is all countable, then the union of them is also countable. I don't know. I don't know if we change if there's infinite many set A, it's still countable. My guess is true because this is a dimension. This is dimension of countable, and this is a dimension of countable in the set A itself, so it must be countable. So maybe we can extend it to goes to A infinite, A infinity as well. And the second correlate here is that n Cartesian product with n is a countably infinite set. And we can understand this by, let's say, this is similar to this one. A, B are countable sets, n countable. So it's just a direct result. And third one is out of very big interest, is a set of rational numbers countably infinite. So previously we say like the integers are countable, which is out of surprise because it seems like the integers have both positive and negative. It must be larger than a set of natural numbers, and we find out we can form a bijection. We can definitely form a bijection between the integer and natural number, which is mean the set of integers is the same size as the is the set of natural numbers, which is our very big result. And this case is even more crazy because rational numbers, they are far more dense, like they have far more elements than integers because between two integers 1 and 2, there's 0 0.1, 0 0.001, 0 0.0000001, and 0 0.3, maybe all of these points between two how to say integers and between two natural numbers. So how can this be true? So we have write a proof about this statement. And it turns out that we just use the property of every natural number can recognize A divided by B for A, B belongs to Z. Okay, so maybe not belong to Z, but belong to N if we only consider the positive natural number. So let's say the rational numbers can be split by these three sets: positive rationals, zero, and negative rationals. And they are because the positivity, negativity, and the non-positive or negativity, they are all pairwise disjoint sets. So we can add their cardinality altogether. Right? So maybe we just need to find the Q one, the Q plus one. So for the Q plus one, there's a bijection from positive rationals to negative rationals. We just set up that. And because we only consider the positive rational numbers, which is in the form of A divided by B, where A, B belongs to the natural numbers because we only consider positive side, and AB share no common factors. This is very important because 3 divided by 6 and 1 divided by 2, they are the same. So we don't want to recount one rational number twice. And there's a bijection from Q plus to N multiplied by N. And this is because we can find the map. The bijection is A divided by B goes to AB. And for all AB, which is in the set of Q plus. So Q plus has the same cardinality as N Cartesian with N, which is countably infinite from correlate 2 as we speak here. So which means Q, the positive rationals are countably infinite. Then then we can also see the corollary 1 here. The union of many countably infinite sets is also countable. And we can see here, Q plus has the same cardinality as Q minus, which means Q minus the negative rationals, it is also countably infinite. And the cardinality of 0 set, which is 1. So it is also countable by the corollary 1. And in this case, because the positive rationals are countably infinite, it cannot be finite at most. So Q cannot be finite Q. The rationals must be countably infinite. So we have solved this like not like imaginable at first theorem, like rational numbers are actually countable. And this fact is very useful in later real number analysis. And we can find out real numbers are not countable, but rational numbers are countable. So rational numbers are like far more fewer than the real numbers. And the graphical representation of the rational numbers are countable is like that. So it goes like so every n-dimensional, there's 1, there's 2, there's 2, 4, 2, 6, 3, something goes on. It all goes on to some very large set here. So and this direction is 1n, and this direction is another n. So it's just like the n to the power of 2, which is n Cartesian product with n, which is countably infinite. And we brings about one new notation probably at the end. So the notation, this one represent the cardinality of a countably infinite set. So every time we see this one, I don't know how to write this character. It's called Alif not. So this one might call Alif, but I don't know how to write it by hand. I just saw that on some textbook. It probably look like that. So the statement of A is a countable set, or A is countably infinite. We can just denote it by that to mean it is uncountable. And yeah, so previously we talked about Cantor's first theorem, and this is Cantor's theorem 2, which is the set of real numbers is uncountable. And this application is very useful in computer science when we design the algorithm for inference studies. So how can we say the real numbers is uncountable? We need to prove like there doesn't have any bijection between R and N, which is really hard. So, but before we have find out like the R's cardinality is equal to any open intervals on real line. So this is probably from the lecture 6. Yeah, the previous one. So we just need to prove there's no any bijection goes from N to I, and I denotes the unit open interval that X is from 0 to 1. And the proving process goes like we want to find an F, and that leads to a it leads to a contradiction in the end. So we can say F is any function from N to I, and Aij denotes the J's decimal digit of Fi, because it's go from 0 to 1, so it doesn't have any digit above 1. So it's all in the form of 0 point something like that, right? And also we can define another function n, which is equal to 0 .m1, m2, m3, and in this form mi is equal to 2. If the aii here like 1, 1, 2, 2, 3, 3, here if this one is 1, we change it into 2, and it's not 1, we change it into 1. So this brings a contradictory, because is the m turns the ith digit from 1 to 2. So there must be some m that is not originally occurred in this form, because the m is transitioned it into 2. So in this case, we say it is going from to some large numbers where the 196 number is 1. It is in this form, but m is changed into 2, and it doesn't happen in this function anymore. So because there's some like some decimal numbers and some range, some codomain that is not being reached. Yeah, it's not range, it's the codomain that's not reached by the Fi. I cannot reach, for example, like 1, and maybe the second is 2, so not 2, so it turns 1. So it cannot reach 0.12 and 0.11 something else at the same time. In this case, we say some codomain is not mapped by f. So for any function f is not surjective, which is not bijective, and in the end we say it's not let me say yeah, the real number is not is uncountable, because there doesn't exist any bijection between the between n and I or n and r. And the corollary of that one is called a set of irrational numbers is countable. And this is very easy to prove. I write the proof here, and the main idea is use the proof by contradiction. Like the I be a set of irrational numbers, and this is true. And because irrational and irrational, they are disjoint. And by the previous probably in page 4 or 5, we say like the two countable sets union of two, like the union of two countable sets, if they are like destroying, then the result is always countable. But R is not countable, so this is a contradiction, which means like the irrational numbers must be uncountable, or it will violate that R is countable, which is violate to Cantor's theorem too. And one interesting case here is because if Q is countable, then Q times Q is also countable. Yeah. So this is true because we say if N is countable, if A is countable, and B is countable, then A Cartesian product with B is also countable. So this is true. So this fact says like all points on the xy plane with rational coordinates are countable. So what that means, like if there's x and there's y and there's some dots, there's some countably many dots in this coordinate, and we just need to find out if we can connect 2 points, that is like AB are distinct point in the xy plane, which is in Q and Q plus 2. So one is here, another one is here. And there's a path that can connect these 2 points, maybe go through this point and doesn't reach any points of a countable in a countable set Q Cartesian product with Q. This is one Q, this is another Q. And this path doesn't reach any countable sets of elements, and it can be connected with these two. And this proves like this is like the fact you can think about the rational numbers is only made of a very small point in the real numbers. And later we'll find out if we take the Lebesgue measure of it, it is the measure is 0, which means all of the rational numbers, we add them all together and find out the length is 0. And this is the first case I think this is the first case we think about is size in this way. Like we cannot find a path to go through it because it's so like have so many gaps between them. Okay, so the last theorem is not usually talked about in most real analysis courses. It's usually a selected content to talk about, which is like if S is a set, the theorem says if S is a set, then S is infinite. And this is if and only if there exists a subset of S, a proper subset of S, such that S is the S has the same cardinality as its proper subset. Cool. So maybe this one, we don't need to consider it anymore. This one, we just need to regret. We just need to focus on this point because S is a set is very general, right? So this means like F is infinite if and only if there exists a proper subset of S such that their coordinate is the same. So this is if and only if, so we are proving the two direction. The first direction is very simple. I would say very simple, so you can look it by yourself later. Because we first suppose this is true and to prove this is true. So if the set is a proper subset of it for a finite, because it's not infinite, so we just assume it's finite and to see the contradiction. Oh, and because it's finite, if it's not if it's a not it says if it's a proper subset, then S must be greater than it, right? Because it contains more elements. So this leads us to the contradiction. So the first direction proves. And the most interesting thing is to consider about the another direction. So first assume it's infinite, and then to prove this one is true. So if it's infinite, then there must exist a proper subset of S such that their coordinate is equal. So how can we say about that? Let's focus on the point here. So suppose S is infinite, then because every infinite set contains a countably infinite set, then there exists, we can say there must exist one countably infinite subset as, well, we say it's like the strange S. Okay, the strange S, because it's countably infinite, we can denote it by S1, S2, S3 to S infinite. And we can define another function goes from S to S itself, such that if Si belongs to this countably infinite S, then it goes from Si to S to I. And if it's not in that proper subset, then Fx is just the X itself. Then we say F is a bijection from S to S, regardless of S, the strange X. Okay. Which is a proper subset. Let's see why this. Let's see why this is true. So F is a bijection. F onto S. So why this is correct from S to this one. Yeah, this might be a point to think about. Bijection. Okay, so when we just consider this one, and it's all of the case. Okay, so if we only consider as difference with strange S, then we only consider this point because this is the point not in S, right? So if we consider this point, then it goes from original element to this element, so it's a proper subset. That's right. So you can say S minus this one minus this element out. So we have fewer elements in this one. So this is also a proper subset of it. And because this is a proper subset of S, and it has a bijection between them. So which means, well, there exists a proper subset, which is the S difference with strange S, and their coordinate is the same. So prove the second direction, and both of the direction is down here finally. So previously we proved the direction goes from this side to S is infinite, and then we prove the converse one. So at this point, all of the cases are talked about, and we are end of our discussion of cardinality.